Hi class, today we're going to be discussing trends and periodic properties. This is the second time I'm trying to record this, or actually third time. YouTube, for whatever reason, wouldn't upload it, and I kept trying, so here we are again. So we're going to discover the trends going down a column or across a period of different things that will hopefully help you understand as we start investigating chemical reactions, why these reactions are occurring. First thing we need to understand are valence electrons. Valence electrons are the outermost energy level electrons. They are what you see here in groups 1 through 8, not counting the transition metals in the middle. And it makes it easier if I just explain it here. Group 1 has all 1s. As you go down, these go to periods 4. They all have 1 valence electron. Does not mean they only have 1 electron. It means they have 1 valence electron. So for instance, let's take a look at lithium. Lithium has an atomic number of 3, meaning when it's a neutral atom, it has 3 protons and 3 electrons. But the only valence electron that matters is the one that is accounted for here. So 1 valence electron, which is 2s1. Valence electrons are responsible for the chemical reactions, the chemical properties. They're the ones that interact in all the chemistry that we deal with. Anything that is not a valence electron is part of the core electron, and the core part of the element. And that involves the protons, the neutrons, everything, and electrons that are not valence electrons. We don't really deal with them. This is probably the only time that I'll bring them up. This is strictly what we do from this point on has to deal with valence electrons, which is everything that you see here in this chart. Now, if I go across over here, these are the noble gases. They fill 8 around the element. So 2s2 to p6. So everything that's in the 2s plus the p6s plus the p's make up the valence electrons. So for nonmetals, you have to include the s's that are over here plus the p's that are over here, where anything that's on this side only involves just the s's. Those for the metals. So if we look at something like chlorine, chlorine has an atomic number of 17, but only 7 electrons, valence electrons, are responsible for what chlorine does, how we understand it with its behavior and properties and reactions. That's the difference. So the group numbers up here represent the valence electrons that are down here, not including the transition metals. Okay, so let's take a look at 1. Calcium. What is the valence electron configuration for calcium? Well, we go 1, 2, 3, 4. I am under 4s, and this is 4s1, 4s2. So it is 4s2 would be the valence electron for calcium. And that's exactly what it is. Now, lead is Pb, so it's one of those that doesn't match the name because it's in Latin, and lead is here. So let's break this down. 1, 2, 3, 4, 5, 6. This is 6s2. We're not dealing with these right now. And we go here. So this is 6p1, 6p2. So my valence electrons for lead are going to be 6s2 and 6p2. So there's 4 valence electrons in total for lead. You must show, if it's anything on this side, you must configure for the S and the P's. Has to show that, or it's an incorrect answer because you're not showing the full valence electron configuration. Now, we're moving on from valence electrons, which you need to understand the valence electrons are responsible for all the interactions. We are going to eventually start joining these up with other elements to show chemical reactions, or octets for sharing electrons, which we'll deal with another time. You have to show the electrons, the valence electrons, as dots around it. It doesn't matter how you show them as long as you don't show them paired up. So as you can see, there's different types here. I tend to draw them like this, but it doesn't matter. You can do them as any of these. The one rule is they cannot be paired up until there's not any more open spaces, and then you pair them up. So 1 to 4 valence electrons are arranged as single dots. So you would put 1, 2, 3, 4 around, and then if you had more than that, you would then start pairing them up. But you leave them single because they're more stable if they're alone. So to make sure you understand this, magnesium has 2 valence electrons. It's a 3s2. And so these are the valence electrons for magnesium. So Lewis symbols, here is a chart also showing now the Lewis structure, Lewis symbols for the elements, not including the transition metals. So you can see group 8, which is the noble gases, have filled octet, because the rule is to try to get 8 around, which we'll cover later. More information on that as we start doing ions. But the rule is that they all are trying to obtain a filled octet like this. Except for helium, it is filled as a duet, and that's exactly what it needs to be. So this is 7. So you have 7 electrons around it. Some are paired. 6, 5, and so forth. You see 1, and it goes through. And you see they're not paired until they get to group 5. Then they start being paired up. So write the electron dot symbol for each of the following: chlorine, carbon, and nitrogen. So here's carbon, here's nitrogen, and here's chlorine. So this is a 4A, so this should have 4 valence electron dots around it. This should have 5, and this should have 7. So if we did that right, that's exactly what you see here. Atomic size. So now we're starting to get into understanding how these elements are not just randomly on here. There's trends to them that help you understand what could happen in a chemical reaction. First thing we're going to cover is atomic size. As you go down a column, a group, it starts as small and it gets bigger. And as you go across this way, across a period, they become small. So if you look at period 2, they're big and then they go small. But if you go down here, it's small and it goes big. Not as big as over here, but still. This has to do with the pull that the protons in the nucleus have on the outermost electrons, and also what type of element it is. So an element that is a non-metal, everything in here in green is a well, not all of them, some of these are not, but everything on this portion, let's say the green, are not as large as these. And that's because the pull of the protons on the outermost electrons are stronger than anything over here. So these are bigger because think of this as a house with 5 floors. If you're down here, you may not always know what your tenants on the 5th floor are doing. So they have free energy. You can't watch them 24/7. So they're throwing parties, maybe doing a lot of stuff that you wouldn't approve of because they're so up on the 5th floor. You may not always see 24/7 what's going on. So they have free range. This is the same thing. These want to leave, so that's why they're so big. The outer energy level is so far away from the proton in the nucleus that these electrons are trying to leave this element. Where over here, these green ones, they don't want to give them up as freely. They're going to hold on to them, and they're going to hold on to them more tightly, so they know exactly that it's going to take a lot of energy to have these to break away. So these are smaller because the pull is stronger. These are larger because they want to leave. Metals tend to want to lose electrons. It makes them more stable. That may not seem right because if some of them are solids, how could that be? But when there's interactions with certain or other elements, some of this stuff happens spontaneously. They want to lose their electrons so they can become even more stable by losing those electrons. Sodium metal, which is number 3, period, is very, very dangerous to work with. It's extremely dangerous. I used it for probably a year while I was in my lab. For those of you that don't know, I still work in a lab on the weekends and sometimes during the week. And I had to use sodium metal. It's extremely dangerous and it is extremely reactive with water. So no water could be anywhere near it because the effects would be just not good. But when it comes into contact with chlorine, it loses an electron, and we understand it as sodium chloride. It wants to lose its electrons. Metals will take electrons. Non-metals will take electrons. Metals will give their electrons, and it makes them stable. So this is a partnership where metals lose their electrons, non-metals take the electrons, and that makes both of them more stable than what they would be by themselves. So as you see here, the atomic size increases because the pull is not as strong, and it decreases going across a period because the pull is very strong. So now we're coming to ionization energy. Ionization energy is exactly what it says in the title, ions. We're dealing with ions now. There's an imbalance of electrons to protons in an element. Metals want to lose their electrons. So sodium is in group 1. has a group 1 valence electron, it's going to lose 1 valence electron. That means that once it loses that 1 valence electron, it now becomes an ion with a plus charge. The plus charge is due to the fact that the protons there are more protons in the sodium atom than there is electrons. So there's an imbalance, and that the charge will always show the one that is the most in that element. So if you have more electrons than protons, there's going to be a negative charge there instead. So the imbalance, the one that has the most, determines the charge. Metals lose electrons. They don't take electrons, so they're going to have a plus charge. And depending on how many, 1 or 2 up there. What I mean is this might have a 2 up here, 3 up here. That tells you how many electrons have left that element. And we'll get into those. They exist. So here, if you have a normal configuration, which neutral for the sodium atom, this is what you would write. Now, everything aspires to be an octet, an octet of a noble gas. So the easiest way for sodium to fill the electron configuration for a noble gas is to lose this electron. So it loses that electron, and now it has the noble gas configuration for, so sodium's here, it loses 1, neon. So it will have the electron configuration for neon, even though it's an ion, and it makes it very stable. You have to remove that out of the electron configuration to show that that electron has left. So the ionization energy is low for metals and high for nonmetals. This is because metals want to lose electrons, so it doesn't take a lot of energy to remove those electrons, and it takes a ridiculous amount of energy to remove one from a nonmetal. It will not give it up. It's going to be a battle to lose that electron. So here's a chart of the ionization energy. You can see that potassium, as it's going down, the ionization energy decreases because these are further away from the nucleus. So it doesn't take as much energy to pull that electron off. Whereas lithium doesn't have that big distance. It's going to take, even though it wants to lose its electron, it's going to take more energy to remove that electron. And the ionization energy increases. So this is the energy you need to remove an electron, because nonmetals do not give up their electrons, and they're smaller radius, so it makes it harder to pull them away from the atom. Metallic character is one that loses valence electrons easily. This is an error, so don't read this last sentence. There's other slides that back up the correct information. Metallic character is more prevalent in metals on the left side, because metals are on the left side, is less for nonmetals on the right side that do not lose electrons easily. Do not read that last sentence. As we go down here, you can see that metallic character increases. Metallic character means loses electrons easily. Doesn't lose electrons easily, everything that starts going across the period this way, because these are where the nonmetals are. So then in transitions have difference, so we don't really count them right now. We're dealing with this and anything that's over here. And as they go down, this has to do also, think about it with atomic radius being large, because of the fact that they want to lose the electrons. So they're going to be larger because they want to be able to, the grasp of the nucleus, the protons, isn't as strong. So that also increases metallic character, which equals giving up electrons easily. And here is a chart to show you everything that I discussed. Maybe I went over something too fast, so here you can read over the information that I've just covered. And ionization energy. So here's a chart with everything I've just discussed. So here's everything, and a lot of this is all joined together. Ionization energy, energy that is needed to remove an electron. Very high over here. You need a large amount of energy in order to remove electrons from non-metallic characters, which are nonmetals. Nonmetals do not give up electrons easily. They will put up a fight. Everything on this side is atomic radius. These are very large metallic character because they want to give up electrons easily. They are metals. Metals do that. And everything that goes in the opposite direction means that these have low ionization energies. Atomic radius is very small, on this side and so forth. So now let's test the information that I've given you. Which is the largest atom out of carbon, nitrogen, and fluorine? So I'm not asking for the largest atom in the periodic table. I'm asking between carbon, nitrogen, and fluorine. These are all on the same period. So if we're looking for the largest atom, atomic radius is going this way, so closer to the metals. So carbon would be the largest atom, which has the highest ionization energy. I'll tell you right now, we don't include noble gases because they are so stable that they just don't react to things. So we're looking at group 7, and it would be fluorine. Fluorine is, I don't know why this has an H here, that's an error. Fluorine, I'll tell you, is has the highest ionization energy. It will take a lot of energy in order for that to pull an electron off of it. That has to do with electron affinity, which we haven't really discussed yet, but it's okay. I don't know if I had it on this one. No, I didn't. This is a different picture, but it means the same. I'll discuss the electron affinity another time, but they go hand in hand. It's exactly what it means. It means that it's love for electrons. It's going to hold on to them. So this is the one that takes the most energy and will hold electrons the closest out of everything here. And then which belongs to group 5. So if we go here, 5A, and that's nitrogen, which is exactly everything that matches. Okay, so now let's do trends. Going down group 6A, here 6A, the ionization energy, and if we look at our chart, we're going against that arrow, so it should decrease. Going across period 3, 1, 2, 3, from left to right, the atomic size, so we're going from here to here, and we're going against the arrow again, so this should decrease. And going down group 2A, the metallic character should increase. So we have decrease, decrease, and increase, and let's see if we got that. And we got that right. Hopefully I did. Well, I sort of know what I'm talking about here. So this chart helps you understand. You're not normally given a chart like this. So this is something that you should become familiar with. Why? Because if we're given a chart like this, then it makes it easy to understand the trends. This is something that you're going to have to understand without a chart, or since we're at home, you have to have this chart for yourself. I will not give this to you because as we start going into further and further chemistry, these are things that you're just going to have to understand the trends. You may not know exactly, when you're looking at two between them, but you should definitely know the trends overall. Okay, thank you.